Right, thank you for organizing and thank you everyone for joining in. My name is Paymaan. I'm a software engineer on the FoundationDB team at Apple. And I'm going to talk about self-healing FoundationDB from gray failures. So hopefully by the end of the talk, you have a better sense of what those terms mean. But at a high level, we have a problem related to gray failures, which I'll define later. And we want to automatically, without human intervention, heal or fix that problem. So the agenda I had in mind was I'll first go through what problem we were trying to solve and sort of distill it down to a requirement. From there, I'll talk about how we solve the problem. And that has two parts. One is the architecture of the gray failure system, the system that solves the gray failure problem. But before that, I think that as a programmer, the interesting part is also how we were able to leverage the building blocks or the primitives in FoundationDB to then assemble and form a simple system that then solves the problem that I'll describe. After that, I'll go through some challenges during this journey, and finally, we will conclude. So in terms of the problem, imagine like an abstract distributed system. You have a bunch of nodes. There's a cluster here on your right. Those are the blue circles. These are your servers. And then there's a yellow client that wants to talk to the cluster. The client talks to the cluster via some API. It generally doesn't know about the internals of what's going on the server side. And the servers are communicating within each other to then serve the client. Now, if there's an issue between two servers, ideally that should not affect the client. But that is exactly what we were observing in certain cases. So let's go a bit more concrete. Here I have something called proxies and logs. So these are part of the cluster, FoundationDB cluster. These are the servers. Proxies are the server that the client talks to when it wants to commit a transaction. The proxy then orchestrates the transaction. And to satisfy the D or the durability in ACID, we have to write the mutation somewhere. And we write them in what we call T-logs or logs. Furthermore, for fault tolerance, we add redundancy to this. And this is configurable. But in this example, you can see proxy writes to 3 logs. OK, so proxy waits for all 3 logs before it can respond back to the client. If there's an issue with a single log, actually the write latency would increase, and the client would be impacted. Another example is between proxies and resolvers. So resolvers are the component in FoundationDB which do concurrency control. So we want to be performant. We want to accept concurrent transactions. At the same time, we want to maintain a high level of isolation or consistency. And therefore, we need to do some conflict detection. And that is what resolvers do today in an optimistic way. So just before committing, we will make sure that there's no conflict. And the paper has more details of what that entails. But at this level, there is pipelining and batching involved. So if there's an issue with the resolver and the pipeline is moving slow, that can actually affect the write throughput as well. So it will lower the write throughput. So overall, a single degraded process can cause write degradation. In this case, a human operator or on-call gets paged, excludes the single process, which then triggers the recovery. And as part of that, we don't include the degraded process again. And the goal of the system we're trying to build is we want to be able to detect and self-heal from such gray failures. So I'm going to scope the discussion to failures which are gray, meaning and this is somewhat of an overloaded term. For the purpose of this presentation, gray means it's not a complete or a hard failure. So it's not like a node crash or a complete network disconnect. Think of this as like a transient network issue. And so our goal is to detect it and then automatically recover from it or self-heal from it. And that's the no human intervention part. This, of course, helps with the operator load, the on-call load, which is great. But the other benefit is that if the system can automatically do the same thing as a human would have done, computers are generally much faster then. And so if we can do it in a shorter time span, then we give a much better customer experience as well because we mitigate quickly. So I'll further scope the problem to only components within what we call transaction system and log system. And within these, you'll see proxies, sequencers, resolvers, log servers. So apart from sequencer, I've discussed these in examples. So this is part of our, in the critical path of our writes when we do transaction commits. And this is where, from experience, we saw most of the issues. I'm going to further scope the kind of failures to network slowness. There could be other kinds of failures as well, and we can extend to that. But because network was the main source of pain for us, that's what we optimized for early on. Okay, so let's move on to building blocks. So these, I've enumerated them as 1, 2, 3, and 4. And they're somewhat independent, so bear with me. But they will come together when we discuss the gray failure architecture. So number 1, unbundled architecture. So what does this mean? A first order approximation of some database is it has 3 components: a component to process transactions, a component to write the logs of the mutations for recovery and durability, that's the WAL val, and a component to actually store the data where you can serve reads from. Some databases, for them, the unit of deployment is horizontal here. So one single node will do all 3 tasks. For FoundationDB, it is actually vertical. So we have a first-class concept in the code base called roles. And the reason is we want to be able to independently scale these components as and when needed. We can always place them on the same machine if we have to, but that's a decision that we make. Okay, so that's number 1. Number 2 is talking about roles, a special role called cluster controller. This is part of our control plane, which I won't get into. Think of cluster controller as a role which has a global view of the cluster. So it has a lot of information about the cluster. For people who have interacted with FoundationDB, if you request status JSON, cluster controller is actually the server that computes that and returns it back. Cluster controller drives a lot of critical operations, and one of them is recovery. I won't go into the details of recovery, but I'll just briefly describe what happens. So recovery happens when you bootstrap a new cluster, or if there's a reconfiguration, or there's some fault and we want to trigger a recovery and go to a healthy state. There are different triggers for it. And when it happens, all the processes in your cluster come up in a state called worker. They then register themselves with the cluster controller. This is an RPC. And they're like, hey, I'm here, cluster controller. And cluster controller then recruits them. Recruiting here means cluster controller assigns a role to a worker. So cluster controller will say, hey, worker 1, you opted in as a candidate, go become a proxy. Hey, worker 2, go become a log. And so cluster controller in this process just has the global knowledge of all the processes, all the roles. It's also a singleton, so there should be only one cluster controller in the cluster. And think of it as like really a central authority for the entire cluster. Now, talking about recovery is pretty fast compared to like some of the other systems that I've worked with. Cluster controller drives the recovery, as we discussed. And although the recovery protocol is fairly complex, if you read the paper, you can get a sense of the complexity. As a programmer building a feature where you want to trigger recovery, it's super easy. It is a common entry point. It's very well optimized. If you want to trigger recovery, it's very easy to do. And it's, as I said, it's fast. Our median P50 is around 3 seconds, which is less than our 5-second timeout. And finally, number 4, this is probably the most independent of the other 3 building blocks, is our transport layer. So we like to, in FoundationDB, historically, have a lot of our own infrastructure. Part of that is maintaining our own transport layer and how we do RPCs. So we have a library where every process, when it talks to its peer, so let's say proxy, when it talks to a log, we maintain an in-memory state of the peer, what we call peer, and the connection for the peer. And in the background, we are actually monitoring the health of the peer via ping latencies. And this is something that's already there. OK, so let's go to how we can assemble these building blocks to create a system that solves the initial problem. So at a high level, gray failure is a complaining algorithm. It's just like humans. So what do I mean by that? So right off the bat, we can just leverage building block number one, the concept of unbundled architecture and roles, because we already know at a granular level that, hey, this is a proxy, this is a log. So I'm using the, if you remember the proxy to log example where we write to 3 logs and 1 log is slow. Here I've just mentioned 1 log for simplicity. Now, if proxy is talking to a log and there's some issue, a transport layer, building block number 4, already has that information. So proxy already easily can know that there's some issue with the log, let's say a network latency issue. Now, at this point, what would a human do? You would want to complain to someone. And the requirement to who you want to complain to would be, I want that person to be fair, right? And to be fair, you generally need knowledge, right? If you don't have knowledge, it's hard to be fair. And so naturally, the candidate for complaining then becomes cluster controller. So proxies would complain to the cluster controller saying, hey, this log is degraded and I don't have a good connection with that log. So that's number 2, the concept of cluster controller and it having the global knowledge of the cluster. Now, after this, cluster controller has to make a decision. It has to be fair. So what does it do? This is kind of like a multi-step process, so I'll simplify it a bit. But cluster controller would first aggregate all the complaints from all the processes. It will form an in-memory state, a map, from the process to the complaints against it. It will dedupe the complaints. So if I complain about someone 10 times, cluster controller would think that's just 1 complaint. And then it would sort these complaints based on the descending order. So in this case, in this example, log 1 has been complained about by proxy 1 and proxy 2. Proxy 1, if there's a symmetric network issue, and this is not always true, but for the purpose of this example, if proxy 1 has been complained about by log 1, and proxy 2 has been complained about by log 1 as well. And the cluster controller would see, well, log 1 has the highest number of complaints, 2. It will mark this as a degraded process in memory. Cluster controller already drives recovery. It's super easy to trigger. Trigger the recovery. And as part of the recruitment phase, we just look at that in-memory state and say, well, hey, you were degraded. I had a complaint against you. I'm not going to recruit you. And so you just don't recruit this degraded log anymore. And some other log ends up being recruited, and you're back to hopefully a healthy state. So overall, fairly simple architecture, 2 parts to it. Processes complain to the cluster controller. A cluster controller tries to fairly decide who to exclude, and it triggers recovery. And it's all automatic. But there are challenges. One set of challenges is what I like to call false positives and false negatives. So false positives are times where the gray failure system triggered recovery, but it should not have had triggered recovery. And the should not have had part comes from what would a human have done. If the on-call decided that there was no recovery needed, the gray failure system ideally aligns with that. But if it breaks that, if it does trigger recovery, and makes a different decision, then that's a false positive. A good example of this is tie breaks. If I complain about someone 10 times and they complained about me 5 times, cluster controller has to decide. It does the dedupe and it sees 1 complaint from each. It's very hard or impossible to decide like what to exclude, me or the other person. And so that's in practice today, we get enough data or enough complaints to break ties. Another category is false negatives. So false negatives is the other way, where gray failure system stayed silent, did not take action, whereas it should have taken action. A lot of times we do this because one of our principles here is that we do not want to make the situation worse. So let's say you have n nodes in the cluster and everyone is complaining about everyone else. You don't want to exclude like half or more of the cluster. Maybe that's not even possible because at recruitment time, you need enough to be able to go to a healthy state. But even if somehow you can recover with half the capacity or less, probably your workload is the same with half the capacity, and that could be an issue. So generally, we avoid cases where we think situation could be worse. Let's say we exclude too much. But there are valid cases where it makes sense. So one example is If all the failures, let's say if you have a fault domain and you have some nodes in it, if all the failures, if there are so many nodes in that domain which are being complained about, there's something wrong with that fault domain, then it could be okay to actually take action, assuming you have redundancy and another fault domain you can fail over to. And so in such cases, it's fine. This requires, of course, cluster controller to have information about what the domain is so it can make a fair decision or a proper decision. This is something we don't do today in gray failure. Okay, another challenge, and this is for what we call HA mode, highly available mode, is this is where you have a primary region and a remote region for disaster recovery. The challenge there is that right now we're focusing on network and latencies. And we need to pick threshold. We need to say, well, P99 of this, more than this, is unhealthy. Okay. For intra-DC latency, the thresholds are fairly easy to pick. For inter-DC latency, however, it's hard because it depends on the physical distance between the data centers, the characteristics of them, and so on. And so the latency signal for these remote processes is not reliable. Actually, to be precise, like any complaint from primary to remote or remote to primary we just cannot pick a good threshold because it's a function of the DCs they're part of, and we don't want custom configurations per DC. It's just not scalable. Primary complaints and remote complaints are fine, right? So if the complainer and the complainee are in the same region, same DC, cluster controller, if we give that information, because we control cluster controller, so we can just write the code and it already has a lot of information, then cluster controller will today only consider those complaints. So if there's a complaint from between primary and remote, those will not be considered because we don't know what a good latency threshold for that is. So that's what I mean by we only consider intra-DC complaints. Now, this does mean that if there's a complaint from remote to the remote, that complaint gets sent to cluster controller, which is in primary, and that's fine. By far, I think the biggest challenge is complexity in heuristics. So as I said, there are two parts to gray failure. There are these processes which are complaining, so they have to decide, when do I send a complaint to cluster controller? At what frequency? What do I exactly include in there? And the cluster controller has to make a decision based on those complaints, and it has to be fair. Now, being fair is complicated. You just ask your manager if they're receiving complaints. And so you just cannot write a few lines of code to fix this. It's based on experiments and trial and error. And so a lot of our logic, our heuristics, have built up over time based on edge cases we have found and cases where false positives and false negatives. And so a lot of complexity exists at this layer, specifically, I would say, at the cluster controller being fair layer. That's fairly complicated today to reason about. And so some techniques to overcome that, first of all, is just better observability. I feel that's something that gets overlooked a lot, but is super critical, where we should have enough metrics and logs to be able to quickly answer, hey, why was the recovery triggered? Whereas it should not have been triggered, or the other way. And so that's one part of this. The other part is we have simulation tests which inject failures. And then we have an invariant saying, well, I inject a failure after some time in simulation, I expect gray failure to take action and they should no longer be this degraded process. And so if you maintain that invariant, simulation then fuzzes the state space of the system with different database configurations and can find edge cases or false positives and false negatives. And the other way as well, where we should not trigger recovery, but a recovery is triggered. So that's something that simulation can help with. And finally, test clusters do the same thing. You can inject faults and make sure we do trigger recovery. So in conclusion, fairly simple design and architecture, but over time, a lot of complexity in the heuristics. This has shown to greatly improve operating FoundationDB at scale. One, just because a lot of times issues like transient network issues are handled automatically without any on-call intervention. But also, assuming we go to the same decision as an on-call would have done, and that's the correct decision, then computers are faster. So we mitigate faster and customers are more happy. So I'll end here, but if you want more details, The FoundationDB paper talks a bit about some of the roles or so the building blocks that I mentioned. And if you're specifically interested in gray failure or in general FTB, feel free to reach out. And that's it. Thank you. Any questions? Oh.
Does the cluster controller ever become overwhelmed with too many requests? And does it become a bottleneck? In that case, how is that handled?
Yeah, that's a good point. In general, cluster controller does a lot. Like just when you request status JSON, a lot goes on in the cluster controller to do that. So we haven't seen cluster controller become a bottleneck just for the purpose of gray failure. But at the same time, just going a bit into implementation details, complaints can come at some frequency, and that's fine, but cluster controller doesn't immediately take action. So it takes action at some cadence of time. And so that helps a bit in terms of not overwhelming the cluster controller. But yeah, in theory, this could be a bottleneck. It's just we haven't experienced that.
Thank you.
Great talk, thank you. What is your heuristic for when to complain?
So today, it's based on, if you look at the code, the source and the destination, right? So if I have a peer and that's a storage server, then we will not send a complaint because our assumption is that storage server, if you know about this, data distributor will take care of it. But other than that, if the source and the destination or the complainer and the complainee are part of the transaction subsystem or the log system based on the paper's definition, we will send a complaint immediately to the cluster controller. But this is done again at a worker level when these complaints are sent. This happens at some time frequency. So after some time, every worker would say, oh, this is my peer list. And these are the ones that are degraded, and therefore I should send a complaint.
I mean, like, what is your actual threshold definition of when you're saying, because at some point in time in this, you have to decide, like, my network is 20% degraded. Is that a time to blame the other side? Is like my network is 40% degraded? Like, what is your definition that you're hitting?
It's based on latencies. So for example, we'll say P99 is greater than 1 second, for example. So if we get enough data points for a peer, P99 ping latency is higher than some threshold, then we'll send a complaint.
There's certain relationships that if you're looking at latency, like the proxy is driving most of the requests. So like if it's a proxy that's a problem and seeing high latency for a bunch of things that it's talking to, does it start outwardly blaming everyone around it, or?
Can you repeat the examples of proxies?
Like, if you're a proxy, you're talking to a bunch of components.
Yeah.
There's not a bunch of things where like a log server is invoking something back on a proxy, or like a resolver is invoking back. So there's like one direction that it seems like a lot of your complaints are going in.
Yeah. Yeah. So
how do you balance?
Yeah, exactly. So going back to the peer example, so proxy has a log peer here, but it's possible that the log is not talking to the proxy. So in this example, only proxy is sending complaints. And so in practice, if there's one proxy that's having an issue and it just thinks everyone else is to blame, it can send a lot of complaints. But at the cluster controller level, we generally have some threshold where we say, well, if we're excluding this log, it should have at least this many complaints, unique complaints against it. So if there's one proxy sending complaint about everyone that it's talking to, we have knobs in place to say, well, at the cluster controller level, this is just one complaint. However, if that log that the proxy is complaining about has also been complained about by 3, 4 other roles, then yes, then we do take action. So this is all knobs and configurations, and this is something we tune. And so one knob is exactly like how many unique complaints do you have against you?
Cool. Thank you.
Okay.
So thanks. That was one of my questions that I wanted to ask. The other is there are basically the straggler jobs that generally require more time to run, and that might be expected. So how do you differentiate between an actual complex job that is taking time and might need more resources and not just a restart? Or basically a new node, it might need more resources. That is one. And the second is, um, till now, I have learned that we just restart that node to maybe that will resolve the issue. Then why, just wanted to know like why restarting doesn't help and we give it to a new node.
Yeah, to the first part, so this is all, the health is based on pings, right? So even if a process is doing some intensive task, um, I believe, and I have to look at the code, that we have high priority for what we call the ping receivers, right? So as the expectation is that even if you're doing some task, you should take time out to return the ping response. And that is what we rely on for measure of health. Because we're focusing on network, right? So something could be taking, valid time on CPU or on whatever, like as long as it can return the ping response in time, they're all good. So that's the first one. The other part is it depends on the failure. So let's say on that process, the NIC has an issue, for example, the network interface card has an issue. So generally what we do is exclude the process, trigger a recovery and recruit a new process. And then we have an expiration. So after some time, that old process is actually it's valid for them to come back to the cluster once we trigger recovery. It's just that we want to play safe early on where we just restart the process, maybe it doesn't work, and then we have to exclude them anyway. So we just directly exclude, because generally we do have in production clusters, a lot of these processes which can take over. Does that answer your question?
Yeah, just one last question. I have just read this in theory that pinging something gets the least priority as compared to the job being done. Is it reverse in our case?
Yeah, I need to, so this all depends on the transport layer, which is already there in FoundationDB, and Grayfield just leveraged it as a building block. I believe we give it high priority, but I'll have to double check, yeah.
Makes sense. Thank you so much.
Okay.
Any other questions for Paymaan? If not, I want to thank you, Paymaan, for this amazing talk.
Thank
Very
you.
informative. Thank you.
Thank you.